Hello again, my dear students, and welcome to the second part of our first chapter related to measurement systems, measurement types, and measurement errors. In the previous chapter, or in the previous portion of the chapter, we have demonstrated together the general ideas of measurement types, different types of scale based on Stevens' model, and we have explored even some associated parameters or associated classifications related to measurements, like, for example, distinguishing measurement between active and passive and so on. Today, as a second part of this chapter, we are going to demonstrate a very important and a very essential topic in the field of measurement, which is the measurement error. So let's start today this presentation, which is actually a continuing to our previous presentation under the measurement errors. Okay, so basically we have to understand a very important note that there is nothing called a measurement system without an error. So it's impossible to get rid of errors. What you are trying to do simply is that you are trying to understand, analyze errors so that you can perform some sort of mathematical techniques in order to minimize its effect. But basically, you will find errors everywhere in your system. And maybe the first question to be asked in this direction is, what are the sources of error? Referring to our system, I think we already see this slide or this block diagram. Maybe we already saw it in the beginning of the chapter. We can say that in general, measurement systems can include or is consisting of three main blocks. First, we have the measurement object or the phenomena to be measured. Second, we have the measurement system, which might be an instrument, a sensor, or whatever. And finally, we have the observer. Considering these two main factors, we can classify the sources of error into three sources, including first what we can call natural error, or between quotations, environmental errors. Natural errors or environmental errors are all errors associated to the system due to uncontrolled parameter in the surrounding environment. So, for example, if I told you, please now go outdoor and measure the solar irradiance using pyranometer, using photodiodes, whatever it is, it might happen that while you are measuring this solar irradiance, a certain variation happen in the solar irradiance due to, for example, an obstacle cloud, simply because you are doing a measurement in an uncontrolled environment. It might happen that due to the relatively high temperature, your sensor starts to get reading deviated with respect to the standard reading. So here another effect. It might happen that due to high humidity, a precipitation of a water vapor layer accumulated on the surface of your sensor, which impacted the reading. So again, it's an environmental effect. So here, all these uncontrollable parameters can attribute to what we can call the natural or the environmental noise, also the environmental error. Additionally, it might have an error due to the instrument itself, which what we call the instrumentational error. And if you return back to my previous part of the first lecture, when I considered the word calibration, if you remember, so the word calibration here is very important. And you can control, or even you can at least recognize your instrumentational error by using the calibration process. So simply, if I have a load cell that measures the weight, and I have a calibrated weight of 1 kilogram, and I put it on the load cell, and I found it 1.05 kilograms, that means I have a 50 grams error associated to this measurement. This is not environmental. This is mainly due to the error in the instrumentation itself used to measure the object. And finally, the error can be due to the observer, either due to incorrect data reading or lack of understanding, so he can or she can make a wrong measurement or take a wrong measurement. So this should be an error due to the observer. So, or due to the observer, I'm sorry. So these are the three factors attributing to error. Let's now discuss how we can classify error. Basically, we can classify error into two types: what we can call a systematic error and what we can call a random. Referring back to the example I just mentioned to you related to the load cell, when I use it to measure the mass of an object, and we found that this 1 kilogram as a calibrated weight well reflected on the monitor of the scale to be 1.05 kilogram. So if I measure 2 kilograms, this 2 kilograms will not be measured as 2 kilograms, it will be measured as 2.05 kilograms and so on. So as you observe, we have some sort of a shift. It looks like, for example, if you are using an AC signal, or if you are measuring an AC signal, and there is some sort of unknown DC bias to this AC signal, so all your AC signal readings will be DC shifted with this bias. This is what we see in the systematic error. So in the systematic error, there is a systematic shift between what we can call the true value or the exact value and the measured value due to some systematic error occur in the system. Usually, this is an instrumental error. Alternatively, if you go to the other side where you measure irradiance, outdoor irradiance, and you make these measurements n time, let's say that you make it 20 times. Sometimes you will make the measurement in a good way because there is no cloud, you can measure everything in a good way. In other times, it might happen that cloud can pass. And whenever the cloud can pass, it might be with a low speed, so it totally upscales the sun radiance, or it might be in a very fast speed, so it's just a spike of wrong measurement and return back to the original measurement. Herein, as you can expect, my dear student, each time you are going to face some sort of what we can call a random error, which doesn't have a certain mathematical way to be described. It's something randomly. Sometimes your reading will be very close to the true value, and sometimes it will be very far, depending on the condition, which is dynamic and which is random. So this is the second way where you can demonstrate your error. Okay. If we try to express this in a mathematical way, considering a very well-known Gaussian distribution for the reading, we can say that a systematic error here, as you can see, so this is not a systematic, I'm sorry, random error, as you can see, does not impact the average reading. However, it extends, it stretches the variance. Simply, as you can see here, we can say that the average of all these points is still in the middle, but the variation between the true value and the other value is very wide. So as you can see here, the average is still centered around the true value, but with a very stretched variance. Alternatively, when you go to systematic error, your variance is very small, but the average is still itself is shifted. As you can see here, the variation of the reading is very narrow, but the average value is shifted with respect to the true value. So this is how we can express the systematic error. Okay. How we can demonstrate error. So for example, if I am measuring a voltage, how should I include error in my measurements? Simply, the process of an error is simply that. If you are measuring a 200 volt using some sort of a multimeter, I tell you that, for example, you are going to measure this 200 volt 100 times. Basically, what will happen is in each time, you are not going to get exactly 200. Sometimes you will get 200, 200.1, 200.2, 199.8, 100.99.9, and so on. So in order to write it in a way that your observer can understand that there is a margin of error, what you can do is you can make it in what we can call absolute error format. So herein, when I write 200 plus minus 0.2 volt, that means that the exact value I measure, or not the exact, let me say, the average reading value I measure is 200. However, after a successive iteration of measurements, these 200 might fluctuate plus 0.2 or minus 0.2. So it is varying between 199.8 to 200.2. This is simply how I express error. On the other hand, we can still write the error in another way, which we call it the relative error. So instead of making it as an absolute of 0.2 voltage, you can make it in a form of a relative as a percentage of the average value. So the same you can write, for example, for a resistance, that this resistance is 500 ohm plus minus 10%. So please expect that the value of this resistance might vary 500 plus 10%, which is 50. So it might be goes up to 550, or it might goes down to 450. Depends on the measurements you captured or you take. So these are the two ways where we can express or we can demonstrate error, either in an absolute way or either in a relative way. But now, one of the most important parameters or points to be undertaken during this session is what we can call the accumulated effect of error. What is the accumulated effect of error? For example, let's give you a very, very simple example. If you are performing Ohm's law, I'm quite sure that all of you know Ohm's law. If you are performing Ohm's law in order to calculate the value of a resistance, so simply what you did in your lab is, let me now turn to the white paper, if you permit me. So here, let's say that I told you, please do Ohm's law experiment and calculate resistance. So simply what you are going to do is you are going to the lab and you are going to put a voltmeter, for example, a voltage source, for example, and then you have here an ammeter in series, and then you have a resistance here, and you will have a voltmeter in parallel. That's true. So what you are going to say, my dear student, okay, so I will measure voltage here, I will measure current here, and then resistance equal voltage over current. That's true. But now, based on our understanding that this V is not V, this V is simply V plus minus delta V, if you consider it in an absolute way, or maybe it's delta V over V if you consider it as a percentage, so you can write it as it is. So it's V plus minus delta V over V, where this delta V over V is a relative error. And similarly, I is I plus minus delta I. So you have an associated error to the voltage, and you have an associated error to the current. What we are searching for it now is what is the associated error for the resistance. This is very important because usually when you are doing experiments, you are doing experiments to calculate numbers that are then inserted into equations. And it might happen that like this case or other cases, that it might happen that we have 2, 3, 4 parameters that are measured experimentally with associated error. And we have a concluding parameter, which is a combination, either by addition, subtraction, multiplication, division, whatever it is, of these parameters. So in order to calculate the overall variation, either absolute or relative error of these output parameters, this is very important. So let's consider some examples. Let's consider some examples. Okay, for example, if we have a parameter called z, where z is equals to a plus b. And we say that a is equals to a plus minus delta a. And b is equals to b plus minus delta b. So as you can see here, I'm expressing a and b in terms of what we can call absolute error. So finally, we need to calculate z plus delta z. Here we can say that this is equals to a plus minus delta a plus b plus minus delta b. We already know that z equals a plus b, so we can skip here z correspondingly to a plus b. So absolute delta z, the absolute error, because remember we are using here absolute. So the absolute delta z equals to what? Equals to delta a plus delta b. Why here I'm using absolute? Because simply I'm expressing the absolute error, if you remember. So typically happen if z equal a minus b. Let's do it together. If z equal a minus b, again, a is a plus minus delta a, and b is b plus minus delta b. So z plus minus delta z equals a plus minus delta a minus b plus minus delta b. Again, absolute delta z equals delta a absolute plus delta b absolute. So either you are making an addition or a subtraction. In both cases, my dear students, you will end up with an addition of the absolute error of the two parameters a and b to get the absolute error in the output parameter, which is z. What if we have something like that? Z equal a times b. Again, a is a plus minus delta a, and b is b plus minus delta b. So what you are going to do, simply, you will say that z plus minus delta z equals a plus minus delta a times b plus minus delta b. Now we can multiply these two brackets together, getting ab plus minus a delta b plus minus b delta a plus minus delta a delta b. Again, we know that Z is A times B. So you can cancel this with this. So what you will find here is that you have delta Z, which is A delta B times B delta A and so on, plus delta B, A delta B. Again, you can divide the overall equation by Z. So delta Z over Z equals. Here we have A delta B over Z. Plus minus. Here plus minus. Plus minus B delta A over Z. Plus minus delta A delta B over Z. Okay, great. That basically is A times B. So if I absolute everything, I can say delta Z over Z equal. Z is A times B. So herein, it's like that I have A times B. A will be cancelled with A. It ends up with delta B over B as an absolute. Plus, similarly here, Z is A times B. B will be cancelled with B. It ends up with delta A over A as an absolute. And here we have delta A, delta B over Z. Let's have a look. This term, delta A and delta B, are the absolute error in A and B, which are basically a very small number. It's an error. And as you know, when you multiply two small numbers, you will get a smaller number. And then when you divide this over a big number like that, that means that this number is going lower and lower and lower. Accordingly, you can cancel this with respect to those two parameters and say simply that delta Z over Z equals delta A over A plus delta B over B. If you remember, my dear student, here, the term delta A over A, here we use it delta B over V, is a representation for the relative error. So simply, it seems like when you multiply A plus B, it seems like you are just adding the absolute error of A to the absolute error of B to get the overall absolute error of Z. So this is the multiplication process. Back to our presentation. So, as you can see here, this is a sum up to what I just proved in the written white papers. So, if we have an addition or a subtraction of numbers, the overall absolute error, which is delta Z, is simply the summation of the absolute errors of the components. So here, for example, we have A, B, C. So it's delta A plus delta B plus delta C. If we have a multiplication process or a division process, the absolute, the overall relative error is simply the overall relative error of each parameter independently in a summation format. Here you can make it more and more, and you can do, for example, you can make by yourself this division example. We make the multiplication together, so we can repeat it for division. And here another example when we consider a multiplication process or even a division process to the power of n or m or l, whatever. You can see that this ends up with a multiplication. So, for example, here it's the relative error of A multiplied by the power, which is n, and the relative error of B multiplied by m, and the relative error of C multiplied by L, and so on. And maybe you can try as a homework or a small quiz to investigate what if we have a lim function, or what if we have an exponential function. So if, for example, if Z equal exponential A, how we can calculate the delta Z as an absolute error in terms of delta A and so on. So please try it, and I will be happy to receive your replies via email, maybe here on the comment of the YouTube or via email if you wish. So this is how we can consider the error due to multiple error factors. Now, let's do together some example in this direction. Okay, so let's start with this example. The example mentioned that calculate the maximum percentage error in the sum and the difference of the following two measurement voltage. So we have a voltages V1 and V2, and simply in the first equation you are going to make it in a form of summation. So V equal V1 plus V2, and the second we are going to make it in terms of subtraction. So let's do this together. So please, you can open your presentation in front of you. So to read numbers, we have V1 equal 100 plus minus 1%. And we have V2 equals 80 volt plus minus 5%. So as you can see, my dear students, we cannot proceed as far as we can say, for example, that V3 equals V1 plus V2. So as it's a summation process or even a subtraction or a difference process, you cannot proceed with the relative error. So you have to transfer this relative error into absolute error. So what we can say that V1 equal 100 plus minus 1 volt, which is the absolute value of 1%, and V2 equal 80 plus minus, here the 1% is 0.8, so the 5% is 4 voltage. That's right. So now you can proceed so that V3 plus delta V is summation of V1 plus minus delta V1 and V2 plus minus delta V2. And as we say, the delta V3 is simply as an absolute equals to the absolute of delta V1 plus the absolute of delta V2. So here we have 1 voltage and here we have 4 voltage. So the delta V3 in absolute is equals to 5 voltage. If you would like to return back this 5 voltage into a relative error, then what you are going to do simply is that your total voltage here is 100 and 180. So delta V3 over V3 is simply 5 divided by 180 as a percentage. So this is relative error. If you repeat the same process, but with a subtraction instead of addition, what will differ here that you are going to use a minus here, but still here you are going to use a plus. So the output will be 5 volts still. So if V4, for example, equal V1 minus V2, still delta V4 equals as an absolute 5 volt. However, as a relative error, delta V4 over V4 will be 5 over 20. Why 20? Because simply the absolute value is 100 minus 80, which is 20. So now the error will be big error to be 25% error. So you can see here the difference. But the same process is applied. So this is simply how you can do either in addition format or even in subtraction format. Another example. Let's see this example together. 820 ohm resistance with an accuracy of plus minus 10% carries a current of 10 milliampere. The current is measured by an analog ammeter on a scale of 200 milliampere range with an accuracy of plus minus 2% of the full scale. Calculate the voltage across the resistance and the power dissipated in it. So let's start to first map the inputs. Okay, just numbering the pages. Okay, so back here. So we have R equal 820 plus minus 10%. And we have current measurements of I equal 10 milliampere plus minus 2%, considering that these 2% is full scale range of 225 milliampere. So maybe the new information or the new knowledge to be observed in this question is the 2% given here is given under the title of a full scale range error, not as a relative error. So what is different between having a full scale range error and a relative error? Let's try to understand this point together. So the main point here is that when we start considering this 2%, we are going to consider this 2% of the 25 milliampere, not of the 10 milliampere. So in order to solve this, let's first return back the relative error of the current into an absolute error. So the absolute error now is 2% of the 25 milliampere. So it comes to be 10 milliampere plus minus 2% of the 25 milliampere will end up with 0.5 milliampere. Now you can return it back into relative error of the measurement, not of the full scale. So you can write that I equals 10 milliampere times plus minus. Here you can make it the 0.5 of the 10. So it is 5%, I guess. So this will end up with plus minus 5%. Now, if we would like to calculate, I think the question asks for the voltage and the power, I think. So the question asks for, yes, calculate calculate the voltage and the power. Okay, so if we calculate the voltage simply equals V equals I times R. So as we already understand together that whenever we have a multiplication, this will end up as a summation of the relative error. So we have 5% here and we have 10% here. So the overall is 15% error. So the overall error in V, which is the multiplication of 10 milliampere times 820 ohms, which is will end up with 0. I think here we have not 0.8 point, sorry, 8.2 volt, 8.2 volt with plus minus 15%. This will be the output. And if we have power, which is I square R, so the delta P over P as a relative error is 2 times 2 here is the power, 2 times the 5% plus the 10%. So it ends up with a 20% error. So the error in the power will be accumulated as 20%, which is again using the equation we studied together. So you can here calculate simply the power and the voltage. Of course, the power here is easily calculated as 10 square, which is 100 milli times 8 times 8 times 820 ohm. So we have maybe 82,000, I think, yes. And then this, we can divide this by 100. So it will end, sorry, by 1,000 again. So it will end up to have power of 82 watts plus minus 20%, I think. And here the voltage is 8.2, is 8.2 voltage plus minus 15%. So I'm sorry if these numbers are not too correct. Maybe I have to double check. So this is 10 milli, 10 times 10 times times 820. So it will be 8,200, and then we multiply it by sorry, we divide by 1,000 for the sake of the milli, so it will end up 8.2 voltage. I think this is correct. And then this 8.2 voltage again multiplied by 10 milli, so it will end up with, I think, 82 milliwatt. I think here this is 82 milliwatt plus minus 82 milliwatt plus minus 20%. So this is 20%, the maximum voltage, so the maximum error in the power, and 15%, which is the maximum error in the voltage. Okay, that's great. Let's turn back to the presentation. Yeah. Sorry. Okay, that's great. So, how we can measure the effectiveness, the robustness of our instrumentational device, or maybe of our sensor? We have two main parameters that are used to measure this process. What we call accuracy and what we call precision. The difference between these two parameters is essentially important to understand what, because maybe in English you can say that this man is an accurate man, or you can say that this is a precise man. Maybe in English we have the same flavor, but electrically or from the measurement perspective, there is a big difference between a precise equipment and an accurate equipment. So precision is for the sake of to what extent these measurements are close to each other. For example, let me say that I'm going to measure the weight of my mobile. This, where is the camera? Yeah, this is, I'm going to measure the weight of my mobile, this mobile, okay? I'm going to measure the weight of this mobile. And I bought a scale, and I insert this mobile phone on the scale 100 times. And it ends up with, for example, sometimes it gives me 500 grams, sometimes it gives me 499, sometimes it gives me 501, and so on. So it seems like all measurements are very close to each other. So this is a precise measurement process. But the question is, when I say that this is a precise measurement process, did I consider what we can call the real value, the true value, the exact value? What is the exact value? Which is the real weight of my mobile phone. So it might be that my mobile phone mass or weight is, for example, 450 grams. But when I consider precision, I didn't consider this for 450. I mainly consider to what extent these measurements are close to each other, regardless the exact or the true value of the measurements. This is a precision process. But accurate process is mainly the comparison of each measurement with respect to the true value. So to what extent these measurements are compared to the true measurement or the exact measurement, which is a very important parameter. So precision is comparing measurements with themselves. Accuracy is comparing measurements with the exact or the true value. And it comes very important to say here that in order to calculate the accuracy, you have to have what we can call the true value. Otherwise, you will not be able to calculate the accuracy. So let's here go with an example. What are we target? Actually, we are targeting both. We are targeting a precise and accurate measurements. So whenever it's a precise, measurement will be very close to each other's. Whenever it's accurate, measurements will be close to the true value. And this is typically what we are seeking for any measuring device. Let's have an example here and let's see how we can deal with this. So let's see this example. Here, okay, we have to turn sharing off so that we can see the camera in a full screen. And let's try to go with here. It told me that a voltmeter is with an accuracy of plus minus 1%. Reads exactly 100 volts. I think we don't need the, maybe in the next examples we are going to need it. But here I think this is a simple example, so we can do it quite easy. Okay, so yes, now to the okay. So sorry for this. So a voltmeter with an accuracy of plus minus 1% reads exactly 100 volt. The true level of the measurement voltage is somehow between 99 and 101. This is correct because whenever I consider accuracy, so I'm considering the variation between the measurement and the true value. So if the measurement is 100 volt and if the accuracy is plus minus 1%, that means that the true value might be vary between 99 volt to 101 volt. Okay. However, in the precision, as I mentioned, we are comparing results to each other's. So here we are comparing the error of measurement over the measurement's value. As you can see in the precision equation, the true value doesn't appear because simply we are comparing results to each other. So for example, let's see this example. If I told you that I measure a distance of 4,200 feet, and I found that there is a variation of 0.7 feet. I did, for example, 100 measurements, and during this 100 measurements, the variation is about 0.7 feet. So simply the precision will be 0.7 over 4,200. As you can see, in this story, we don't have a true value. We don't know if this 4,200 is true value or not. All are measured values. So we make some sort of measurements and it ends up that the variation is 0.7. So the precision is 0.7 over 4,200. Okay, so if we did an experiment, so let's do it together. If we did an experiment that, for example, I measured this distance 5 times, and I found that the first time it gives me 4,150. The second time gives me 4,205. The third time it gives me 4,215. And the third time it gives me 4,210. And finally, it gives me 4,195. As you can see, each time I got a different value for the distance. How can I calculate the precision? So simply, to calculate the precision, we have to calculate what we can call the most popular value, or the MPV, which is a very simple way of calculation. What you have to do simply is to sum all values and then divide them over the number of measurements. So for example, here we implement 5 measurements, as you can see. So simply what I do, which is a very basic, natural, unbiased averaging, I'm just summing all these values and then dividing them by 5. I will get 4,188, which is the most popular value or the average value. Now, what should I do then? Then I can calculate what we call the variance. Maybe you already hear it about the variance in your probability courses. I'm not sure if you already have considered a probability in your curriculum or not, but it's very simple to calculate. It's in a very simple manner. It's the measurement minus the most popular value all square over the number of measurements, which is 5. So we can calculate it in a very easy way, as you can see. So let's do this exercise together. So let me now stop on just down the full screen, and let me open an Excel file here. And let me start writing the input. So I can also turn off the camera because we no longer need the camera. So we can just write numbers. So we have here, okay, we have 5115, sorry, 4115. This is the first reading. The second reading is 4205, 4205. The third reading is 4215, 4215. And the fourth reading is 4210. Sorry. And finally, the last reading is 4195. In a very simple manner, if I would like to, so this is reading number 1. And this is reading number 2, and so on. So the MPV is simply, as you can see here, is a summation of these values divided by the number of reading, which is 5. So as you can see, this is typically the same number we got in our lecture slides, which is 4188 feet. Okay, this is the MPV. Now I need to apply the equation of the variance. So simply, each iteration, first I subtract the measurement from the MPV. So as you can see here, so here this column will be measurement minus MPV. Okay, so what I will do here is just this equals this number minus this number, and I can just $sign the second cell to fix the process. So here, okay, and then we should square it, equals, not equal, I'm sorry, we can just copy this. So this is simply the square process, which is equals this to the power of 2. So this is very simple. So as you can see here, I'm just squaring. I think this number already, you can find it in the next slide. Yes, typically, as you can see here, this is the square here. And finally, we need to sum all these numbers again to the equation. We need to sum all these numbers and then divide it by n, which is the number of iteration, which is 5. So here what we should do is simply sum so let's do it here, equal this is the sum, and finally we need sigma square, which is the variance, which will be this number divided by 5. So this is the sigma square. I'm sorry. So sigma, which is mainly the square root of this number. Sigma, not square root. So sigma is equal square root of this number. It will be 37.09 sigma. So this is simply how you do the process. So as you can see, you can calculate sigma or the variance in the number. Maybe I have to double check which one is correct because I found it here. I found it here 60 or 80. It's 80. Here it's 85, and here it's 37. So it seems that there is an error either here or there. I think this equation is correct. And then I think this is also is correct because we divided by 5. And then this is, I think also this is correct. So it might be the error here. I will double check which one is correct. But in all cases, we can see that there is a very systematic process in order to calculate. I think, yes, numbers here are correct. So up to this stage, we have identically the same numbers. Maybe in the consequent process, we will figure out where the problem. But in all cases, I will try to solve it. Maybe in the next video, I'm going to check with you. Maybe this number is not correct. I'm not sure. So I have to double check this. But here you can see that we have evaluate the divergence in the measurements. Again, when we do this experiment, we don't know the exact or the true value. We are just comparing results together. So my suggestion here that for you, just try to repeat the same process or the same experiment, but with excluding the 5115. Why we should exclude the 5115? Because if you observe, my dear students, the 5115 is what we call the extreme value. All other four values are typically very close to the 4,200 value. The only extreme measurement is the 4115 measurement. So this 4115 measurement stretch the variance, mislead the most popular value. So if we make the same experiment, so let's do it together now. If we go here and do typically the same process, except that I will just make this copy, Control C, and we go here and make it down here. And what I'm going to do simply, my dear students, is that I'm going to delete this row. Okay, so now this MPV is divided by 4, not 5, because we have only 4 measurements. Again, you now can see that it's very close to 4,200 with respect to the previous one. Okay, and then we make the squaring and everything is correct here. And then we can do that this is again divided by 4, not 5. And again, as you can see here, this is the square root of this. So it ends up with a sigma of 19.69, while the first one was 37.09. So simply you can observe the difference between these two numbers to find that when you exclude the extreme measurement, this narrow down your diversity, increase the precision of your measurement, and show you better performance. So this is very important when you do measurements, to observe by naked eye, to observe measurements, because usually you can either manually or now using some data cleaning algorithms, even some AI algorithms, you can clean your data to make the measurements more precise and to exclude those measurements which definitely observable that they are wrong measurements, like the 4115 measurement in our case. So let's turn back to our slides. Great. So this is the precision and this is the accuracy. My final slide is something very, very important. If you remember, we consider that we can have an error either due to the natural environment or due to the instrument or maybe due to the observer. And this is one of the limitations. This is a scaled glass bar where you have a scale. This scale, for example, we have a zoom in figure showing that the scale, this is 15 and this is 20, and these are 5 breaks in between. So it's 15. So this is 16, 17, 18, 19, 20. But now the water level is something between 16 and 17. So you will not be able to pick up exactly what is the value. It might be 0.6 or something like that, or it can be, it's something greater than 17 and lower than 18, something in between. You will not be able to observe it in exact. So here you will have some sort of roundup to approximate a number between 17 and 18, but it's not an exact number. So this is another sort of error that may be due to the limited capabilities of the observer. Our eye will not be able to exactly scale the level between 17 and 18. So we have to round it up somehow, a number between 17 and 18. And this is again another process. So now we have finalized the process of errors. And also one of the sources of errors may be only also due to the resolution of your device, or maybe due to the range of your device. What is the resolution? So, for example, if you buy a multimeter with one digit after decimal display, so the maximum or the minimum value you can measure is 0.1 variation. It will not be able to measure smaller than 0.1. If it's 2 digits after decimal, so it's 0.01. If it's 3 digits after decimal, so it's 0.001. So the larger the number of decimals is the number of digits after decimal, simply the higher the resolution. So for example, here I consider the voltage is 1.2, but it seems like the exact voltage is 1.231, which means that I ignore 0.031, which is considered as an error, mainly due to the limited resolution of my instrument or of my sensor. So this is another way. And another important thing is the range. So you have to make sure that your readings are within the range. This is typically happen when we measure voltages using a multimeter. So if you measure a voltage in the voltage range using a scale of a millimeter or a scale of again, I'm sorry, if you are measuring a voltage in the millivolt range and you put it in the scale of the volt range, then you will get a reading which is totally inaccurate because you are choosing a wrong range. So you have to go down to the appropriate range, which is the millivolt range. So this is again important to consider. In the next chapter, we are going to study the first set of devices, which is the analog devices. I think that most of you already know what are the difference between analog and digital. So what we are going to consider is analog devices. We are going to consider analog voltmeters, analog ammeters or current meters, and how to measure resistance and all this stuff. This will be in a separated chapter, inshallah. So thank you very much for your concentration in this direction and looking forward for a new chapter. Thank you very much.